Welcome everyone. You are joining us for SPAD arrays and cameras, a comparison with conventional image sensors and detectors, presented and hosted by Photonics Media. Today's speaker is Milo Wu, the Business Development Manager at PI Imaging Technology. In his current position, Milo connects cutting-edge SPAD research with real-world imaging. Alongside his numerous degrees, Milo brings deep expertise in nano devices and single photon detection. A quick note, feel free to ask questions in the chat at any time. If you experience technical issues, try logging out and back in. You'll receive a link to the webinar recording in your inbox after the session. With that, let's welcome Milo Wu.
Hello, everyone. So I'll be sharing my screen now with the presentation. Okay, great. So I'll start my talk. So Haley already made the introduction. So I'm Milo from PI Imaging. I'm the Business Development Manager, and in my daily work at PI Imaging, a size company, I help customers from large cap company down to university labs to check if SPAD arrays are useful for their specific applications. So first, I'll make an introduction on SPADs and also some detectors in general. So how does optical sensor work? It's typically converting photons into charges and with certain amplification. So once photon arrive, you have charges, and this will be collected into certain intensities. And how this camera works is that you have a lot of pixels of these detectors, and the electrical signal, which represent the intensity, will generate this image. So every pixel has different intensity, which creates this image that we're used to. So a different concept that SPAD use is that it's operating over breakdown. So when there's a single photon arriving, you create an avalanche current, and this creates an infinite amplification of the signal. So what this gives at the output of the SPAD is that a single photon turns into an avalanche current, which gives you a high output, which is 1. If there's no photon, there's no current, then you have 0. So basically, SPAD is a photon to digital transformation that gives you only zeros and ones as an output. So this gives you the capability of photon counting, and because it's digital, there's no readout and no excess noise, and it's extremely fast. So what does a 1-bit information look like? So in this image, this is a 1-bit image. It means in this image, you have only zeros and ones. So how do we use this information? If we accumulate more 1-bit image, you can put together many 1-bit image into a multi-bit image, and then it will become an image that we are used to, which is typically an 8-bit, 12-bit image, and you have certain dynamic range. What SPAD can also do is time tagging, as it's super fast. So a single photon, if you combine it with a timing circuit, you can get the time tag. So this time tag can usually be down to having a picosecond timing resolution. What you can do with the SPAD array is that you can also do time gating. So time gating is basically synchronizing a pulse light source with the SPAD. So you open a very short exposure time with respect to this pulse light source, and you can create this time resolve imaging methods. So in this video, we're syncing a pulse laser with the SPAD camera, and you can see basically the laser pulse traveling in space is captured with the time gating method. So now I'll start some comparison with the conventional photodetectors. So this goes through some APDs, which is avalanche photodiode, PMTs, and SIPMs for the single pixel or small array detectors. And I'll also compare the SPAD cameras to SCMOS, QCMOS, and EMCCDs. So to address to all these type of detectors, we have basically three product lines. That's point array, linear array, and cameras. So the point array will be comparing to the smaller detectors like APD or SIPM. So typically when we are working with APD, it's operating in linear mode, which means there's a finite gain of this multiplication process. So this results in readout and excess noise. And these detectors are not easy to scale, and it has lower timing precision. So APD is typically much cheaper than other technology, and it's useful for application that really has one photon. So if you don't expect more than one photon, APD can still be a cheap solution for you. For SIPM, it's basically SPADs connected in parallel. So you will have readout noise at the end, but you will not have a spatial information because they're all connected in parallel. So you have one output, and it has low timing precision. It's typically a cheaper solution than SPAD array for a larger detection area with applications. So PMT is a much older technology, but it's very solid and very well developed. So this is the mechanic working principle is that arriving photon will create a primary electron with a photocathode, and this will generate secondary electrons through these diodes, which is act as amplification. What you will see in PMT is that you always need a huge volume of vacuum tube, so it makes it very unscalable. So compared to SPAD, even though they're much more expensive, typically it's possible to replace several PMTs with the SPAD array to reduce the cost. At the end, it might be price effective. PMT has an advantage in its detector area at the moment, but for SPAD, it has much higher timing precision, higher peak efficiency, and again, there's no readout and excess noise, and very low after pulsing. If we compare PMT with SPAD under, let's say, 15 impinging photon situation, you can see a small advantage over PMT. But if you lower the impinging photon count, you will see that SPAD starts to have better signal-to-noise ratio compared to PMT. So if we compare to all the other photodetectors, SPAD has the first is its higher timing precision due to its Geiger mode operation and digital output. There's absolutely no readout noise, no excess noise, and low after pulsing, and it's highly scalable. So the drawback of single SPAD pixel is that it has limited dynamic range due to its dead time, which is typically in the tens of nanosecond range or 10 nanosecond range. And it's also quite small in terms of detector area. So the solution to overcome this dynamic range is to always have an array of SPADs instead of having a single pixel. So now we compare the SPAD cameras to other high-end scientific cameras. Let's first start with the EMCCD. So the EMCCD advantage is that it typically has high sensitivity in the 80s, 90% range, and it has low effective readout noise because the readout noise will be effectively divided by this gain of the EMCCD. And the key disadvantage is that it's slow, so you can probably reach maximum 100 frames per second in full resolution, and you have this multiplication excess noise. So if we compare the SPAD performance with EMCCD in terms of signals to noise ratio, when EMCCD has working in a low gain mode, you will see that the SPAD signals to noise ratio is better than EMCCD in a low light regime. So this is typically below 200, 300 photons per integration. You will see advantage of SPAD in terms of signals to noise ratio. When there's more photon, the EMCCD will be better due to its higher efficiency. Now, if we work in a higher gain mode of EMCCD to lower the effect of readout noise, you will see that the performance of the two cameras are starting to converge. So they're very similar in low light regime, but if you work in a high EMCCD gain mode, you will lower the dynamic range because in EMCCD you will simply saturate faster than the SPAD camera. So in short, when you have SNR advantage in the SPAD, the SPAD will work better in a low light regime. When you work in a high EMCCD gain, dynamic range will be the SPAD array's advantage. Another key advantage is, of course, the speed. As mentioned, EMCCD has a top frame rate of maybe 100 frames per second, but this can be easily beat by SPAD arrays, which can give you easily 1,000 frames per second. So in this experiment, we're checking moving fluorescent beads moving at the same speed. You can see that SPAD can capture at least an order of magnitude more frames than the EMCCDs. Now we can go into SCMOS or QCMOS, which is what's called by Hamamatsu of their SCMOS cameras. So these are the key advantage of these cameras is that they're relatively faster because the pixel logic is in the pixel itself. There's no excess noise due to no amplification like as in the EMCCD. The key disadvantage is that you could have mismatch in the column amplifiers, and this creates non-uniformity. And of course, there's still readout noise components. So if we compare SPAD versus SCMOS in a, let's say, normal lighting condition, you will see the comparisons very close. But if you lower the lighting condition, you will see that SPAD cameras start to show its advantage in signals to noise ratio, especially in a super low light condition. So if we quantify this to SNR again, you can see that SPAD is again excel in low light condition, typically below 300 photons per acquisition. So in this graph, you can see this is here is 300 photons within this acquisition. You can see that within this range, SPAD always have a signals to noise ratio better than the CMOS camera. And of course, above this, the CMOS camera will be better due to higher efficiency, same concept as the MCCD. In conjunction with the high frame rate or low integration time, you can see that if the SPAD is working in a slower or longer integration time or slower frame rate, in here 5 milliseconds of integration time, you can start to see the degradation of SPAD performance due to the dark count, which is analog of CMOS cameras dark current. So we always encourage the user, if they want to switch to SPAD, their application has to be somewhat fast in terms of integration. So in that case, the dark count will not be a part of will not take part in degrading the signals to noise ratio. So here's the comparison video of a SPAD versus Hamamatsu QCMOS done by a distributor in the US. So they distribute both our SPAD camera and the QCMOS from Hamamatsu. You can see that without pixel binning, you can see that our signals to noise ratio is more than an order of magnitude higher than the QCMOS. But since they have a smaller pixel size, it's fair to have pixel binning for the comparison. So they start with having a 2x2 pixel binning, which the SPAD camera still shows a bit better SNR, and even in the 4x4 binning, the SPAD shows a better SMR. And with the binning, you can already see some column amplifier non-uniformity in this data. So the conclusion of this comparison is that if you have application that requires high speed, SPAD will be better. If you can afford having low bit depth, SPAD will be better. But if you have, let's say, longer exposure or you need higher dynamic range in terms of bit depth, then the QCMOS camera could still be better. So this graph concludes what the comparison that I just mentioned. So EMCCD typically has the highest peak efficiency, but all the other cameras other than SPAD has redundant noise and either redundant noise or excess noise or at the same time. SPAD can also work in gating mode, so you can have very short exposure time down to nanosecond, and you can have a picosecond resolution of shifting the gate. So basically for a time resolved application, SPAD basically have a picosecond level of timing resolution. And SPAD has its unique 1-bit mode, which can offer up to 100,000 frames per second of frame rate, which is still much faster if you operate it in an 8-bit mode. So here's a video of what 100,000 FPS look like for a high-speed application. So in the standard 8-bit video, you will see this kind of motion blur due to a longer exposure time. But if you lower the bit depth down to 4-bit or 1-bit, you can see with the super high frame rate, you can achieve almost no motion blur, and you can capture very fast events. So to conclude this section, so currently SPAD cameras still have lower resolution compared to CMOS and EMCCDs, but in terms of speed and photon counting fidelity, there's no, the SPAD cameras will be much better in terms of these specifications. So in our company, we produce, as mentioned, the point array, linear array, and cameras. So the point arrays, we have SPAD 23 and SPAD 93, which is a small arrays of 23 or 93 pixels. Typically, this is used for scanning applications or photon counting in a small region of interest. We also have linear arrays that consist of 320 pixel in a line. This is typically for spectral applications. And we also have cameras from 512 to 512 by 512 to a megapixel SPAD cameras. So all the product comes with the standalone software that can help with data collection. You can get a live view of the image or the counts. You can stream out the photon counts. You can check the time tagging data from the smaller arrays, which gives you around 20 picosecond time resolution. And for the camera, you get a time gating function with also 20 picosecond timing resolution. So applications typically, so as mentioned, we're now part of Zeiss Group, and microscopy is one of our largest customer base. So this is an example from PicoQuant, where they use SPAD 23 for image scanning microscopy. You can see a very huge improvement of the resolution when switching to SPAD arrays. For wide field fluorescence lifetime imaging, also provided by PicoQuant, this is typically for live view, let's say, surgical assistance. You can see a live view of fluorescence lifetime image with the SPAD camera in in a decent frame rate with fluorescence lifetime information included. So the SPAD-23 was also used in the very advanced microscopy technique called stimulated emission depletion. So this is done by the leader in this field, Iberia. You can see the comparison between standard STAD and using a SPAD array to perform STAD. You can achieve a much better resolution. A lot of our customers in the academic area or in the industry is in the quantum space. So this includes application in anti-bunching, coincidence correlation, quantum random number generation. And we also see a lot of quantum computing companies gaining interest in SPAD arrays. So here are some academic journals that's using our SPAD cameras to achieve quantum imaging applications. For industrial application, especially in low light, high speed, this is typically linked with surveillance or other high speed applications. You can see with a standard low light camera, you will typically suffer from motion blur in nighttime condition due to a longer exposure time needed. But for the SPAD camera, you can do it in a lower bit depth mode, and adding on top of that some software solution, which is here provided by UBSET, you can see the huge improvement of the video quality. And on top of that, if you apply it to, let's say, automotive plus, let's say, machine vision application, you can see that this high-speed application, high-speed capability of SPAD arrays helps you to get a much better image quality so that you can apply machine vision technique on top of it. And last but not least is that the HDR capability of SPAD. So this video is recommended to be viewed on an HDR capable display. So you might not see a huge difference on your screen now, but you can still see a huge difference between, for example, when you see a lamp passing by, you will see this very typical bleeding of the CMOS camera, but in SPAD this doesn't exist also. So SPAD cameras gives you a much higher speed imaging capability under low light condition. On top of that, it gives you HDR capabilities. So I recommend you to go to YouTube and check out these video on your other screens so you can really see the difference. So the key takeaway of the talk is that why do you want to switch to SPAD sensors? So there's actually only three key situations that you will want to switch. So when your application absolutely need a higher readability of low light signal, and you need it to be working under high speed, and you need the timing information. In this three key scenario, if you match 2 out of these 3 keywords, we will strongly suggest you to check out SPAD technologies. So on our website, you can also find this table, basically showing you how what kind of working condition is suitable to work with photon-counting mode or time tagging mode or time gating mode. On top of that, there's also a table suggesting whether you should go for the point sensor, linear sensor, or image sensor. But typically, point sensor is used for, as I mentioned, low area scanning applications. Image sensor is used for wide field imaging applications. And linear sensor is typically for spectroscopies. So a quick market projection of the future of SPAD cameras and SPAD arrays is that we believe it will 100% replace PMTs in the long term once the detector area problem has been solved. this will be the key, and it will probably take over 10% of the high-end or scientific camera market, and there will be a broad penetration in microscopy in the very near future. So that concludes my talk. Thank you very much for joining today, and I will be opening for questions.
Thank you, Milo, for that great presentation. As Milo said, we now have time for a few questions before we wrap up. If you haven't already, please type your questions or comments into the chat box. The first question I have is, can you clarify what you mean by exposure time and integration? With a SPAD, are you summing across multiple frames to get an integration, where a single bit frame is an exposure?
Yes, so they're basically, yeah, it's a different term, but it means the same thing. So basically, let's say if you're using a camera, the total integration time of an 8-bit image consists of 255 1-bit image, and the total integration time is basically the sum of all those 255 1-bit image, the exposure time. So it's the same concept.
Great, thank you. The next question I have here is, what is the spectral range? Does the sensor reach the UV down to 200 nm?
So typically this cuts off at around 300 nanometer. As the detector we use is silicon based, so it typically has a visible wavelength range.
Okay, next question I have is, what is the spectral bandwidth?
I think that's a very similar question. So it's in the visible wavelength.
Okay.
So yeah, that's for the silicon SPAD, and of course, if you switch the material, you can have something that can reach 1550 if you choose other material. But in our company, we are focusing on silicon base.
Okay. Next question I have is, will this technology move to mid-wave?
To mid-wave. So yes, so as I mentioned, it's a very similar question. It's basically depending on the material used. So if you switch to 3.5 material or silicon germanium, then you can reach 1550 without a problem. But of course, there's a lot of engineering work needed there, which is not our company's focus.
Okay, next question I have here is, in what price range are SPAD image sensors?
So image sensors, this is typically similar to high-end EMCCDs. So you can have cameras from 25,000 to 50,000. This is the price range.
Okay. What is the ratio of active to dead area for 1 pixel?
Active to dead area. So typically, so all our product has microlens option. So with the microlens, you can typically reach 80-90% fill factor. Without that, it's probably in the 15 to 20 range. But we also develop microlens, so this is typically in the 80 to 90%.
Okay, next question I have is, do you have software to perform the correlation measurement, or the user needed to provide this?
Typically, this is done by the user. What the user can get from our software is all the time tags, if you have the time tagging option available. Then with the time tag, you can either compare between the pixels or even between two different detectors if you sync them with the external trigger.
Okay. The next question I have is, thank you for your wonderful slides. I'm currently a student in university. Could you introduce us about the current situation in the job market?
In the job market of SPAD arrays or
I assume SPAD arrays, just because there wasn't any clarification beyond that.
Okay, so there's probably only 5 or not more than 10 companies in the world that's working on SPAD at this moment. So I would say at the moment it's very limiting. But yeah, but this will definitely ramp up because we also see a lot of competitors popping up. So I guess this will change in the near future.
Okay, next question I have is, will this work for 1100 nm?
1100, yes. For the visible, no, for the silicon one, it's probably cutting off at around 1000. So I would say no for the silicon. But again, if you go for other materials, let's say silicon, germanium, you can reach this wavelength.
Okay. Do you offer or plan to offer SPAD arrays with MIPI interface?
So if there's enough budget, we can do customized interface. So MIPI is definitely within our capability, yes.
Okay. The response and SNR for these camera varies a lot in function on single line wavelength in the operation range. Visible? Question mark.
Sorry, I don't get the question. Can you repeat?
Yeah. The response and SNR for these cameras varies a lot in function on single line wavelength in the operation range. And then in parentheses, they have visible? Question mark. So I believe they're asking if it's visible.
So all our comparison in the SNR, let's say that I present, is within the visible range, yes. And it's typically, let's say, we compare it at the maybe in the green wavelength.
Okay, last question I have is cooling using thermoelectric technology used to improve resolution?
So cooling helps with controlling the noise. If you cool the camera, you have lower dark counts. So in our sensors, there's a Peltier cooler in the box, so it's maintaining the sensor at room temperature to not heat up over room temperature. And this is to help with the noise. It doesn't help with the resolution.
Okay, thank you. If we don't get to your question today, don't worry. We'll follow up with you via email. And if you think of something later, feel free to reach out to us at webinar@photonics.com. Before we go, I'd like to thank our presenter one last time, Milo Wu, and all of you for joining us for SPAD arrays and cameras, a comparison with conventional image sensors and detectors. This webinar was presented and hosted by Photonics Media. Thank you all so much.
Thank you.